So what this says is that the way the system moves through the phase space, the motion through the phase space, stays on surfaces of constant h. The trajectories through phase space stick, so to speak, to surfaces of constant h. There are many surfaces of constant h. As I vary the value of h, I make different surfaces through here. I'm not going to try to draw another surface on top of that. But the point is, once the energy is fixed, the system will continue to travel on that. Talked about was the harmonic oscillator. For the harmonic oscillator, the Hamiltonian was omega, just a number. So the two-dimensional space, P and Q, we write one equation, P squared plus Q squared is a constant. That defines a circle, which is one less dimension. We have different circles corresponding to different total energy. And the way the system moves or behaves with time is wherever you start the system, it will stay on the same circle, just orbit around that, around the origin. So that's another idea that surface. Yes.
Okay. You've got four equations there. P squared plus four equations. So what I'm saying is, I'm trying to see. So for P and for Q, you got one equation. Is that what you're saying, or two equations?
The equations of motion are these. There are two equations of motion. It follows from these two equations of motion that the time derivative of the energy is zero. That says that or the time derivative of the Hamiltonian. That says that the Hamiltonian is a constant in time. So let's call that constant E. Okay? The constant, of course, is determined by the initial conditions. Whatever the initial energy is, that's what E is. And each value of E corresponds to a surface in the phase space of one lower dimension. The rule is the motion of the phase point, let's call this the phase point, through phase space, stays on the same surface of constant energy. That's one of the many consequences of these equations here. That the motion is on a surface like that. Okay?
The way you present this, there's really no relationship between the P's and Q's. This is just all very axiomatic.
Yeah. Well, there's nothing there. No, really. by these equations. Right. Yeah. Yeah. No, that's right. For example, there's no automatic assumption that P is equal to the mass times Q dot. Right. Take whatever the Hamiltonian is, and we'll work out some examples which are non-standard. But basically, the Hamiltonian can be any function of Q and P. In many cases, you can write it as a kinetic term, that's what P squared is, plus a potential term. But by the time we've gone this far, we can write many, many other kinds of Hamiltonians. The only question is, do they correspond to anything in nature? The answer is often yes. But now, as you say, I think you put the right word on it. The axiomatic, this is an axiomatic theory now of mechanics, or a formal structure, or whatever you want to call it, and that defines it. Okay, so now let's move on to the idea of a flow in phase space. Let's go back to the harmonic oscillator for a minute. And instead of taking a given initial condition, a given starting point, a particular starting point, for example, this point, and then watching the phase point move around in a circle, let's imagine all possible starting points and indicate them by points on this plane, and in fact think of a sprinkling of them. It's not uniformly distributed through here. Every one of them moves. And in the back of my mind I'm thinking that the sprinkling of points can be thought of as a fluid. Not a real fluid, but an imaginary fluid composed of a huge dust. Think of it as a dust, but a fluid dust, where all particles of the dust move in a way which is dictated by these equations. So wherever you happen to be, you'll be at the next point a little bit later. You'll move in some way, and some way is dictated by what the Hamiltonian is. And so you get a pattern, a picture of a flow. In this case, for the harmonic oscillator, the flow is very simple. Just everything sort of rigidly moves around on a carousel, so to speak. Everything just rigidly moving around. And so the fluid has an extremely simple kind of motion. And it's not important whether this is a fluid, whether any real fluid could move like this. This is a secondary question. Just picture it as a fluid, or a collection of a dust moving around like that. More generally, for an arbitrary phase space, always even dimensional, but I can't draw an even dimensional, you can play exactly the same idea. That the phase space is filled up with a dust. The dust corresponds to every possible starting point, and then just start the clock and let it go, and the dust moves through the phase space and defines a flow of a fluid, a flow of an imaginary fluid. We're interested in the fluid, and we're interested in the properties of it, but we're interested in one very specific property. The property called having a divergence or a convergence of a flow, a divergence of a flow.
You said it's a rigid thing, so you're implying that they all have the same period.
In this case, they all have the same period. Period. Yes, that's exactly right. And what is a period? It's it's determined by this frequency. Well, this is a harmonic oscillator. Harmonic oscillator, no matter how far you displace the coordinate, it oscillates back and forth with exactly the same frequency. So right, so that translates into the statement that everything moves around rigidly. Right? Exactly so. Alright, so now we come to just a little bit about flow vectors. Flow vectors and how they're connected to this and the properties of those flow vectors. A flow vector is a very, very simple idea. Incidentally, we're imagining a flow which is a kind of stationary flow. Points move, Their motion, what they're doing next, only depends on where they are on the phase space. where this particle moves next. In other words, what its velocity is. Not the velocity q dot, but the velocity in the PQ space. What are the components of the velocity? What are the components, first of all, of position in the QP space? Q and P. Okay? What are the components of the velocity in that space? Not the honest velocity of mechanics, but the velocity in phase space. Q dot and P dot. So we make a little vector out of them. All the Q dots and all the P dots. Q dots and line them up. Q1 dot, Q2 dot, blah blah, P1 dot, blah blah blah, line them up and make a vector. Make a thing whose components are the vector. And then that velocity vector can be thought of as a vector in the phase space. A vector in the phase space showing the direction of flow. What is the flow? It's just these P dots and Q dots. This is the velocity vector, and they're given entirely by known functions, if we know the Hamiltonian, known functions of position in that space. The right-hand side are known functions of the position, which are determined by the Hamiltonian. And so it means whenever a point in the flow gets to this point, it always has the same velocity. The velocity being determined by the value of h and its derivatives at that point. Alright, so that means that we can take this space and fill it up with a vector field. A vector field just means a vector at every position. At every position in Q and P space, in phase space, we draw a vector which is just the velocity of the phase point if it's at that point. Kind of an ugly drawing I made, isn't it? Well, okay. Let's draw it for this guy over here, for this system. Is the velocity the same at every point? The velocity is not the same at every point. Even at a fixed radius, the velocity is over here in this direction. Do I have it right, or is it clockwise or counterclockwise? I told clockwise, isn't it? The velocity is this way here, this way here, this way here, this way here. But suppose you're moving closer. Then the velocity is smaller. The magnitude of the velocity is smaller. It goes around in the same amount of time, but it has a smaller distance to go around. So the velocity, this is not a very good circle around the origin. This circle around the origin, the velocity is smaller here. As you go in even closer, the velocity is even smaller. And so we fill the space up with a velocity field. Here it's this way, here it's this way, and so forth. And that's called the velocity field of a fluid. It's called the velocity field of a fluid. And it's just a collection. It's nothing but these guys over here, P dot and Q dot. Okay. Now, the question I want to ask about this fluid is whether it's compressible or not. Whether it's compressible or not. Now, what does compressible mean? I'll tell you what compressible means by starting with an example of a one-dimensional example. Supposing I have a fluid which is a one-dimensional fluid. In other words, it's just a collection of points moving along one-dimensional axis. The fluid moves, and what I want to know is whether the points of the fluid get squeezed together and spread apart. In other words, whether the fluid is compressible. If the fluid is strictly incompressible, that means it has a constant density. You cannot change the distance between neighboring particles. For example, if the particles were little billiard balls, well, a one-dimensional billiard ball is a little weird, but one-dimensional little billiard balls, and they were up against each other, and there was no room between them, then you couldn't compress the fluid, and let's assume you also can't stretch the distance between them. Then we would call that an incompressible fluid. Now, an incompressible fluid, if we take the velocity field, at every point there's a velocity, and the velocity depends only on where you are Is it possible that the velocity could vary along this axis? Well, if the velocity varied along this axis, I think it's pretty apparent. But for example, supposing the velocity was relatively small over here and then jumped to something big out here, it's pretty clear that in the region where the jump took place, the points would have to be spreading apart. The points would have to be spreading apart. So the only way to have an incompressible fluid in one dimension is for the velocity to be absolutely constant and independent of where you are. It could depend on time, but we're assuming explicitly that the Hamiltonian doesn't depend on time. And so an incompressible fluid would be one for which the velocity vector had to be absolutely constant. So one aspect of the incompressibility is that if we